Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be showing you how to find the pH of mixtures of weak acids. So what do you do when you have two weak acids mixed together with different Ka's, different concentrations? How do you determine the pH or the H plus concentration of such a mixture? First thing you want to do is look at the acids, look at their Ka values, and determine if one of those acids is much greater or stronger than the others. If that's the case, then you can ignore the other acids in the mixture and just focus on that one as contributing by large the majority of the H plus, such that the others will contribute some H plus or hydronium ion, but it's negligible compared to the other ones. So you can ignore their contributions. So let's begin with a couple of problems. In the first problem, we're going to take this mixture of HF and HClO and see what the pH is going to be, and then we're going to then take that information and find the ClO concentration in that mixture as well. Okay, so the first thing you want to do is if you haven't been given the balanced equations, you need to write them out for each of the acids. Here we have HF and HCl, so HF reacts with water to give you H3O plus F minus. HCl reacts with water to give you H3O plus and ClO minus. And then you can't forget water, right? Water auto-ionizes, so you always got to take that into account. So the two water molecules, one passes hydrogen to another one, gives you H3O plus and OH minus. And here are the Ka values of the acids and the Kw value of water. And so right away you could see that the Ka value of HF is much greater than that of the Ka value of HClO, and also much greater than that of water. So this is about on the order of 10,000s greater, right? So we can just focus on the HF to the exclusion of these. We can ignore the contribution of these because compared to HF, these are going to be fairly negligible in their contribution of the hydronium ion to solution. So then what we're going to do is we're just going to do our ice chart looking at HF. So if we do our ice chart, okay, so the initial concentration of the HF is 0.300, and again, we're ignoring water. Water is not part of the equilibrium expression because it's a liquid, and liquids and solids are not part of the expression because they don't change their concentration. And plus, water, you have so much of it compared to the acid, so we have to take that into consideration. Okay, so we start with 0.300 molar HF, and to start off, we have approximately 0 concentration of H3O plus. There is some in there, but it's practically 0, and we have 0 F. So H3O plus is 0, and the F is 0 as well. So again, we're paying attention to this equation here. These other two we're ignoring for now. So 0.300 HF, 0 H3O plus, 0 F minus. And then the change, since we have 0 product here, according to Le Chatelier's principle, we're going to go towards the product. So that means we're going to lose X amount of our reactant HF, and we're going to gain X amount of our H3O plus, and we're going to gain X amount of the F minus. And so we add these together to get our equilibrium expression. So this is going to be 0.300 minus x, and this is going to be plus x and plus x again. And so now we can write the equilibrium expression, our Ka value expression. So here Ka is equal to 6.8 times 10 to the negative 4, which is equal to these two, the concentrations of the product over concentrations of the reactant, right, raised to their stoichiometric coefficients. So here we have H3O plus and F minus over the concentration of HF. And we're going to plug in our equilibrium expressions here in terms of x. So then this is going to be these two, x times x, that's going to be x squared over this expression here, 0.300, 0.300 minus x. And again, we can do the x is too small approximation. And we could see that that probably is going to be valid because if you look at the Ka value and you look at your 0.3, your initial concentration of the acid, this would be 3.00 times 10 to the negative 1. This is 6.8 times 10 to the negative 4. That's a difference of about a factor of 1,000. So that's probably, it's a safe bet that that's going to be a good approximation. But we can do the 5% rule to just make sure. So let's get rid of the negative x or the minus x here. Again, the x is too small approximation is basically saying that the amount of H plus that is formed is not going to change, or the amount of x that is lost, right? So if we're losing a certain amount of HF, what we're saying is that the amount of HF that we lost in the reaction is going to be very, very small compared to the amount we started with. So basically, we would still end up with practically 0.300. So so this is going to be 6.8 times 10 to the negative 4. So all we have to do now is multiply both sides by 0.300, square root both sides, and we get x. And so there, x ends up being, where's x? 1.428. 1.428 times 10 to the negative 2. And we're only allowed 2 sig figs in our answer because we got 2 sig figs here. Okay, so this is x. We could validate this by dividing this by 0.3 and multiplying by 100. So when we do that, we get, so when we do that, we get x, So we take this amount, we're going to divide it by the initial amount, multiplied by 100. So 1.428 times 10 to the negative 2 divided by 0.300 multiplied by 100. And we're going to get, what is that, 4.8%. So we get 4.8%. So it's less than 5%. So our ionization, our percent ionization is less than 5%. So it's a good approximation. Okay. So almost, barely a good approximation. So just a little bit less than 5%, but good enough. So now we have our H plus concentration, and we want to find the pH. So we want to find the pH. So this is our H plus concentration. So all we need to do is take the negative log of this. So the negative log of 1.428 times 10 to the negative 2 becomes 1.85. So the pH is equal to 1.85. And again, one of the things I want to point out really quickly is, again, we're only allowed to have 2 sig figs here. So when we do the log of something, the sig figs translates into decimal points for the log. So if I have 2 sig figs here, then I should have 2 decimal places for my log, for the pH here. Okay, so that's it for the first part. So we found the pH of this mixture. What about finding the ClO minus solution? Okay, so let's go ahead and take a look at that. So I'm going to have to erase the work we did here. Okay, and we're going to have to do another ice chart, but this time we're going to have to start with initial amount of our H plus. So the H plus we found in the first part, let me write that down again. That's X was equal to, or the X, which is equal to the concentration of H3O plus, was equal to 1.428 times 10 to the negative 2. Okay, so this becomes our initial amount of H3O plus. So we're looking at this equation now. This is the one we're looking at. So we started with 0.100. So 0.100 molar of our HClO, and then we are also starting with this amount of H3O plus, because that's the amount we got from the HF times 10 to the negative 2. And then we're starting with zero amount of the ClO minus. So this is our initial concentrations that we're starting with. And then we're going to find out, well, how much of this is produced. Again, we're going to lose some because some of this is going to dissociate. So we're going to lose some X, and we're going to gain a little bit more acid, H3O plus. We're going to say plus X there, and then that's also going to be plus X there because it's a 1-to-1 ratio. And then we add these together, 0.100 minus X, and this is plus X, and this is plus X. And again, we're going to put these into our expression. Now we're going to use this expression here. So Ka is equal to 2.9 times 10 to the negative 8, which is going to be equal to, this time it's going to be H3O plus, and it's going to be ClO minus concentration all over the concentration of HClO as a reactant. Okay, so then what we're going to do is we're going to solve for this. And so this is going to be, again, 2.9 times 10 to the negative 8 is equal to X squared over 0.100 minus X. We'll do the X is too small approximation, then multiply both sides by 0.100, square root both sides, and then you're going to get X is equal to, it's going to be equal to 5.39 times 10 to the negative 5. So that is your